Everyone, and welcome to this week's Crunch seminar. In today's talk, we'll have two people. We have two speakers. Our first speaker is Dr. Steven Rodriguez. He is a staff researcher, scientist in the computational multiphysics group at the US Naval Research Laboratory. His primary research area is reduced order modeling, which focuses on developing mathematical, numerical, and computational frameworks to accelerate high fidelity simulations and enable HPC caliber simulations on a laptop. His work spans a wide range of reduced order modeling applications, such as accelerating additive manufacturing simulations, traumatic brain injury simulations, and rotorcraft simulations. Prior to joining the US Naval Research Laboratory, Steven had a visiting scientist position at the University of Washington, hosted by Professor Stephen L. Brunton, and held internships at the NASA Langley Research Center and the Caltech NASA Jet Propulsion Laboratory, where he worked on structural acoustics research and on the Mars 2020 rover, respectively. Stephen graduated with his PhD in 2018 from Lehigh University under the advertisement of Professor Justin Jaworski, where his dissertation research focused on rotor fluid structure interactions and rotor dynamics. In today's presentation, he would be presenting a topic titled Enabling Rapid Meshless Multiphysics with Hybrid Data-Driven Projection Tree Reduced Order Modeling. You can start, Stephen.
Okay, thank you so much for that introduction. I didn't realize how long it was until you read it out loud. I probably should have done a little shorter one. But anyways, yeah, thank you so much, everyone. I'm so excited to be here virtually. I actually have a lot of fond memories of Brown University. Actually, I attended an ICERM workshop back in February of 2020. So right before the pandemic really closed everything down. So in other words, the last academic in-person bonding experience I had was at Brown. So, I have fond memories, and hopefully I can visit Brown soon, in person at least. Like Sundata mentioned, today I'll be talking about presenting a class of reduced order modeling techniques that my colleagues and I have developed for meshless methods that are often seen in the sciences and engineering. So before I even get started, I want to thank my co-authors, collaborators, and colleagues at the Naval Research Lab, Athanasios, John Steuben, John Nikopoulos. And a lot of the inception of this work was actually done while I was at the University of Washington. So this is kind of like the foundational work was with Steve Brunton and Kevin Kralberg. And then finally, Liam McGargle, who's actually a PhD student at Lehigh and was interning with us in the summer, really helped out with some of the simulations that I'll be showing today. Okay, so hopefully you guys can see my screen still. Is everything working okay?
Yes.
Okay, great. Okay. So I want to begin with laying some of the context and motivation behind our work. I hear you guys know a lot about physics and for machine learning. So I'm sure, you guys know why we do reduced order modeling, since it's very similar. So there are really two schools of thought in computational sciences and engineering, not necessarily two schools of thoughts, but two tasks that we can perform as computational scientists. The first task is mainly performing high fidelity simulations or high performance computing, where in this scenario, the end user is interested in uncovering some sort of underlying physics, right? In this scenario, the end user is willing to invest computational cost, effort, and resources. And so these tasks obviously are performed a few times in some sort of parametric setting, because you can't really run millions of simulations using high performance clusters or something like that. So I'm showcasing this HPC application with a simulation my colleague ran for a traumatic brain injury project that we had a few years back. We're here, I guess we were interested in really understanding the physics of the traumatic brain injuries that some soldiers may encounter in combat. On the other hand, we have something like a multi-query application, where in this scenario, we're interested in deploying simulations to perform something like design optimization, uncertainty quantification, or other multi-query tasks, basically. And in this sense, we're actually interested in deploying simulation anywhere from 1,000 to maybe 10,000 times online. And so, of course, this is not really feasible to employ high performance computing, as I alluded to before. Because it would incur just astronomically high costs, right? And so in this scenario, the alternative is to employ low to moderate fidelity simulations many times over in the optimization task. And so to overcome this, bottleneck of using high fidelity simulations, I'm sure you're familiar with this, is, we can use reduced order modeling for these types of applications, which, reduced order modeling in the context that I'm presenting today is basically a method that accelerates simulations through dimensional compression or sparse regression over dynamical system solution manifold. So, here the manifold is learned from sampling some sort of high fidelity simulation and kind of learning the features and kind of dynamics that really dominate these physics. Okay, so this is how I'm defining reduced order modeling in this setting. And so the desiderata for reduced order modeling, or wish list, if you will, is basically to enable the use of high fidelity simulations for multi-query applications, and basically enabling a low dimensional representation of a high dimensional system so that we can deploy them in multi-query settings efficiently. And so another part of this, wish list is to avoid incurring additional error due to the approximations that we make in the dimensional compression for the sake of speed up. And so the main train of thought in reduced order modeling, traditionally speaking, has been an Eulerian approach, where a lot of these methods that we see today, like Petrov-Galerkin projection techniques or Galerkin projection techniques, or even some of the work that you guys have done in physics-informed neural networks, is done on an Eulerian-based setting. This is with finite elements, finite volumes, or finite differences. But a lot of the work in meshless context has not seen the light of day with a lot of machine learning technologies. So if you're familiar with the smooth particle hydrodynamics method, or any vortex discretization technique, or discrete element method, these methods can be thought of as Lagrangian methods. And all of these actually have not really been applied to model reduction techniques or any of the physics-informed machine learning techniques to the level, at least, of these Eulerian methods. And so this is really what our contribution has been in the field of model reduction in this setting. Is we've actually introduced a class of model reduction technique to address meshless methods. And so I want to focus a little bit more on the different types of modeling that we do in our lab, which is called the Computational Multiphysics Systems Laboratory, or CMSL for short. So of course our group is called the Multiphysics group, but seriously, we do all the types of physics around. We do anything from additive manufacturing to traumatic brain injury simulation that I showed you, to fluid structure interactions, and we even do things like post-processing of additive manufacturing builds. We do vortex dynamics, and recently we've been getting to smooth particle hydrodynamics for things like naval architecture engineering. So if you're a practitioner or a student of computational sciences and engineering, you probably can use some sort of your genetic brain algorithm that's built into your brain to kind of figure out that this is two different types of modeling. You have the mesh-based modeling and the meshless modeling here, right? So these are the different types of models or approaches that we use in our group. So I kind of want to describe these two schools of thought in a descriptive setting. So let me actually explain what the difference is between mesh-based and meshless computational methods. And I'm going to do that through the classic flow passive cylinder example. All right, so I'm sure that we all know that modeling like fluid structure interactions, complex geometries, free surfaces, and multi-phase flow problems isn't really straightforward. And since our group encounters a lot of types of multiphysics, it's important for us to kind of look into the different types of methods available to us. So the differences in here are, the mesh-based methods, which I'm sure that we've all dealt with at some point in our career, whether in school or if you're a practitioner. We've all dealt with mesh-based technologies, whether that's like finite elements or finite volumes, and they're basically widely used in mature technology. They've been around for decades now. The only issue here is for some of the applications that we work on in our group, we try to deploy some simulations for real-time applications, say, for example, in a digital twin setting. And using mesh-based technologies actually requires more of an intrusive pre-processing technique, or a pre-processing approach, where you might even need a human in the loop to kind of verify and validate the meshes of this. For example, say we have a topology optimization problem or a design optimization problem where we're trying to minimize the drag on this bluff body here, right? So we're going to go through different shapes. We might go through an airfoil or a diamond to try to see what best optimizes or minimizes drag in the scenario. But every time that you change shape, you're going to have to change the mesh. And this is something that meshless methods actually are good at. We don't actually have to kind of move around the mesh too much because the mesh here is actually introduced through a Lagrangian setting where you introduce particles or collocation points into a domain that adapts and reacts to whatever the geometry exists or whatever geometry is in the domain. One downside to these meshless methods, though, is that they can scale very poorly because of their adaptive and reactive nature. They actually have to communicate with the neighboring particles in the domain. So that means that they have to gather information from a predefined, neighborhood. So this is kind of what the summation sign here represents in the meshless formulation, as opposed to the semi-discretized form that I'm showing here for mesh-based designs. This summation really describes the interaction between neighbors. And at worst case scenario, you actually end up scaling quadratically with the number of particles in the domain to actually solve a simulation, which could be really, really bad for millions of particles, right? Because you're going to scale a significant amount. So let me actually describe why these methods scale very poorly with this descriptive example. So if we look at mesh-based designs or mesh-based methods and we look at their specific nodes, say here we're only interested in a very simplistic low-order discretization scheme where we only take into account a few neighboring nodes. If we go ahead and try to start building our discretization matrices, say our mass matrix or stiffness matrix, we're going to end up seeing that we generate banded discretization matrices. It's very rare in finite elements or any of the other mesh-based techniques that you build a fully populated matrix in the actual formulation of things. And so this is actually what one of the main differences between mesh-based and meshless methods is that if we zoom in on this meshless technique here on the right side, we end up seeing that the neighbors of a specific particle are a lot larger. The number of neighbors are a lot larger than what you would normally see in a mesh-based technology. And in fact, H can actually end up, being infinite, meaning that you actually have to take into account the interactions between one particle and the entire neighborhood and domain, right? So this is actually what would result in a dense discretization matrix due to this pairwise interaction between sources, also known as neighbors, neighboring particles and a specific target. So this is basically the reason why meshless methods can scale very poorly. But we are optimists in our lab, so we're trying to make sure that we focus on the pros of these meshless methods. So let me actually leave this right here. Okay, so some of these meshless methods, like I mentioned before, they're adaptive, reactive to whatever the physics are. So there's no need for adaptive and verified and expensive meshes to be, kind of intrusive in the modification of them online when we're trying to deploy these methods, say, for example, in real-time applications. These methods, the formulation is relatively natural or simple, relatively speaking, to formulate things like multi-phase problems and free surface flow problems. And actually, we'll show you two simulations on these types of problems in a couple of slides. Yeah, the computational domain is self-adaptive and reactive to the formulation. And these actually, these methods are highly amenable to parallelization. The formulation is very natural to parallelization, which is really nice. And these are the pros that we'd like to work on, kind of take advantage of. One con that I would like to mention of these methods, again, I actually alluded to this a couple slides ago, is that the maturity of these methods is actually kind of primitive. Maybe that's a bad word to say, but there's a lot of work to be done in the foundational work of meshless methods because they're not as popular as mesh-based techniques, but they are very versatile. And so if you're interested in learning more about meshless methods, we could definitely talk offline. But like I mentioned before, meshless methods haven't really seen a light of day when it comes to reduced order modeling or even physics-informed machine learning. So there's this field is very rich in a lot of work that we can do to improve on, from the foundational formulations to application and deployment of machine learning techniques on these types of simulations. So one particular method that we've been focused on applying in some of the applications in our lab is the smooth particle hydrodynamics method. As I alluded to, we work with a lot of multi-phase flows, and this is an example of a mesh-based technique that we used, that we simulated with COMSOL, a finite element suite for different multiphysics. This is a three-dimensional multi-phase flow, and here you have a two-dimensional multi-phase flow, and Unfortunately, I don't have the actual mesh to show you, but I mean, you can imagine here that keeping track of this interface between the different fluids would be very complex. On the other hand, you have things like the smooth particle hydrodynamics method, and here I'm showing a non-Newtonian simulation where keeping track of this interface that you're seeing along the fluids is actually very natural because you're keeping track of neighborhoods. You're not necessarily keeping track of interpolation points or grid points and the interfaces that exist between interpolation points. So here, everything's adaptive, reactive, and it's a very natural form to think about these types of problems. And so this is really one of the reasons why we've been trying to focus on SPH. And towards that end, we've actually been trying to familiarize ourselves with, using an open source code. If you're interested in using, SPH quite easily, you can Google this, Duals Physics. It's very simple to run. They have even post-processing code that you can import things on ParaView and things of that nature. So these types of problems are pretty straightforward to simulate, and this is one of the reasons why we've been interested in SPH. And on top of that, we're actually building our own multiphysics suite as well for SPH. Okay, so now that you have a little bit of context about what meshless methods are and why we're interested in using meshless methods for some of the applications that we do in our lab, let me build some more context in the actual application of meshless methods and how we're envisioning reduced order modeling being applied in multi-query context, specifically in additive manufacturing. So in our group, we do a lot of additive manufacturing. We do anything from the micro scale to the macro scale modeling of additive manufacturing. And the reason why we're so interested in additive manufacturing from a defense point of view is that additive manufacturing provides versatility in manufacturing of complex components. Say, for example, in a turbo machinery, engineering design or something, we have very complex, jagged and sharp connection points here that may be difficult with traditional, that may be difficult to generalize across different designs with traditional, extrusion manufacturing. But additive manufacturing is very versatile in the sense that it could really generate different types of manufacturing geometries, right? And so this is just an example of types of components that we're interested in with additive manufacturing. Another pro of additive manufacturing is that we can produce functionally tailored components for specific purposes and performance. So think about, a truss, which is technically, topologically optimized in, a civil engineering setting. We can actually generate topologically designed, trusses to minimize weight and maintain, the same strength as a full block of cement or something, or in this case, we're doing with steel. Basically, what I'm trying to get at is that additive manufacturing can really help customize specific structures for specific performances in some sort of optimization setting. One of the cons to, or technical challenges, I should say, because like I mentioned before, we're optimists. One of the technical challenges facing additive manufacturing is that we're trying to quantify unexpected or unique material behavior that affects the functional performance that we've, kind of optimized for. So in the context of additive manufacturing, think about all the laser interaction as it's melting, some of these, powder metal materials. You're going to encounter very sharp heat gradients, meaning that these heat gradients leave high residual stresses behind as they're cooling rapidly, right? As the metal cools rapidly. And so that could actually be detrimental to the performance of the actual truss that you're building, for example. And so what we're trying to do is control, these types of adverse behaviors. And so the question really becomes, how can we tailor functional performance via process control? And this is all to say that one way that our group is envisioning process control in additive manufacturing is through a digital twin construct, where here what I mean by digital twin is anything inside of this red outline, which is basically a digital counterpart of whatever's happening in the manufacturing process. So, kind of our wish list is basically to generate a mechanistic model that is able to perform control or process variable control in real time as it's communicating to the additive manufacturing component. And here we're using, this is actually a discrete element simulation, but we can do things like the smooth particle hydrodynamics method to kind of capture the free surfaces a little bit easier and more of the multiphysics simulations here. And so to kind of begin looking at this digital construct, the question that we've been trying to address is how can we deploy rapid and real-time multiphysics modeling to enable this digital twin framework for additive manufacturing. And the way we've been going about this is actually looking at the literature for reduced order modeling and exploring recent advances in model reduction techniques, specifically intrusive model reduction techniques for different reasons, but yeah, we have our reasons. And so in exploring these types of techniques, what we ended up seeing is that there might be a need for us to extend recent developments in reduced order modeling technologies, specifically for the meshless techniques that I was talking about earlier today. And so revisiting some of the pros and cons that I mentioned before about meshless techniques, the question to overcome the elephant in the room, this expense of the meshless methods has been a key issue for us. And the way we try to address this is looking at traditional meshless technologies that accelerate meshless techniques, specifically what you would call hierarchical decomposition, or they're also known as tree methods. And these types of methods are actually kind of primitive data science algorithms. Actually, they're very similar to unsupervised classification techniques, like, for example, k-nearest neighbors or single linkage type of algorithms. The only difference here is that you're kind of clustering about a specific point of interest based on some sort of distance from a specific target point. In this case, it would be a target particle. We also looked at using fast multiple methods, and this is actually a top 10 algorithm of the 20th century. It's a very nice technique, actually, and it was very popular in accelerating some of the meshless technologies. But in our applications, where we're looking at trying to achieve near real-time deployment, this method wasn't capable of achieving our complexity requirements. And so because these methods didn't work, we turned our eye to projection-based model reduction techniques, which I'm sure you're familiar with, things like the Galerkin projection, DIME, UDIME, and GNAT methods, and so on and so forth. But these methods were traditionally not built to overcome meshless techniques, specifically because of their pairwise interactions, the interactions between the target and the source particles. And so this is really where our contributions have come into play. We developed a class of reduced order modeling techniques called projection tree reduced order models, where we really combine the best of both worlds, from the meshless acceleration techniques to the mesh-based acceleration techniques. And so thanks for bearing with me. Now I can actually start talking about model reduction. So this is kind of me building the context of how our method works. So this is just to show that we're combining projection-based reduced order modeling with 3D composition methods. And so I want to start off explaining our methodology by beginning laying the foundational work for reduced order modeling in the traditional sense. And I'm going to do that with an additive manufacturing problem that we've developed with our suite called Multiphysics suite. It's a play on SPH and physics, like we saw in the prior suite. But this is our version of our smooth particle hydrodynamics code. And so here we're working on the heat deposition equation, where we're modeling heat conduction with an additional, for example, heat flux that we're applying down here below. This is actually a nonlinear equation because we're introducing temperature-dependent material properties. So the conduction, density, and specific heat are all dependent on temperature. So this actually ends up being a nonlinear problem. And so I'm sure your group is very familiar with the residual form of the time discretization of a time continuous equation. So this actually becomes an important residual, which we try to minimize in a projection-based model reduction setting. So this is just to show the formulation of the full order model that I'll be talking about in the next couple of slides. Okay, so let me talk about projection-based model reduction really quickly. And I'm going to go. This is very foundational work. It's been around for, I think, almost 10 years now. And I'll be going over reduced or least squares Petrov Galerkin projection. So in any model reduction setting, step one is always to build a snapshot matrix so that we can train an algorithm, right? And here what we do is we train an algorithm based on some sort of parametric space that we're interested in. And in this setting, we're interested in, say, for example, a parametric inverse characterization problem where we're trying to identify the laser heat profile, the flux profile of a specific laser, and we're trying to identify the velocity at which this laser is passing over a specimen. So we're doing some sort of inverse characterization problem that we have to call multiple times in some sort of optimization loop. So step one is to train our algorithm through some sort of design of experiment, whether that's a greedy algorithm or Latin hypercube sampling technique. We store this into some tensor, unroll it, and perform, your vanilla, singular value decomposition to get dimensional compression out of it, right? And so here we can extract the spatial, representations or features that are very important to this dynamical system, and perform what I like to call data-driven separation of variables. And the reason why I like to call that is because we're basically separating the state vector in spatial features and temporal features that live in some sort of low dimensional embedding. And so if you're familiar with the Galerkin projection technique, at this point, you would actually substitute this affine approximation into the original ODE and perform orthogonalization via this phi transpose matrix. But here we're actually using the least squares petrov Galerkin projection, meaning that we have different test and trial functions. And so what we actually do is we substitute this state vector approximation into the actual residual and perform residual minimization so that we can evolve the dynamical system in a low dimensional embedding. However, this scales with the intrinsic dimensions of the full order model, so we have to imbue sparsity into the minimization problem using hyperreduction, which is really a term that was coined by the Stanford research group with Charbel Farhad and some of the other French schools like Yvonne Madej. So here we're using this hyperreduction matrix to kind of enable rapid computations of our additive manufacturing simulation. And building that hyperreduction matrix is actually very similar to building the state vector approximation that we used before, except instead of not only taking into account the state vector training, we're also taking into account and collecting data from the residuals. And we actually perform some sort of low dimensional representation of the residual too, using this POD basis of the residual. And the reason why we do that is because we try to formulate some sort of sparse residual linear regression problem so that we can approximate this actual residual using data that we've leveraged from the offline training. And so what you see in this residual approximation down here, this set of operations in matrix operations ends up being a matrix that we defined prior to or in the prior slide. And this is actually what's called the Gauss-Newton with approximate tensors approach, which is actually that was derived originally by Kevin Karlberg back in 2011, and this is actually built for finite volume methods and works very well for our setting because we're actually using a fixed meshless technique because in this sense the point in these particles are not moving in space. Okay. And so performing some sort of, hyper reduction, we can see that we can perform the physics computations on these red particles. And these red particles, you perform this residual minimization, but even though you're performing on these red particles, you actually have information about the entire domain at any point in time in the simulation. You can actually just query a specific point that you're interested in. And so we actually have a paper that we're currently writing on this inverse analysis in additive manufacturing, and hopefully this will be out in the archive at the end of the year. But here we have this additive manufacturing inverse problem that we're working on, and here this is the full order model that was performed on 14 cores with hyperthreading and had almost about 400,000 particles. And the reduced order model was performed on 1 core with hyperthreading and had about 10,000 particles. And the reduced order model offered about over 200x savings in CPU hours. And so the error actually, and this was actually less than 1% in the quantities of interest. And the dirty secret here is that this was actually a reproductive experiment, right? So we actually try to reproduce the exact training point. But we've actually deployed this exact same algorithm in a parametric setting where we actually run the reduced order model on points it wasn't trained on, and we saw very similar results as far as the quantities of interest error. So we're pretty excited about that paper, and stay tuned for that, which hopefully will be out in the archive in a couple of months here. Unfortunately, additive manufacturing is not fixed in space. Particles move around in smooth particle hydrodynamics. And actually, within a few weeks of starting at the Naval Research Lab, one of my colleagues told me that additive manufacturing is not multi-physics, it's all the physics. And that's because you have to take into account phase changes. And this is kind of what you're seeing here, the change between solid and fluid. Red is fluid and blue is, solid, and anything in between is kind of like the molten phase. You have phase changes, you have solid mechanics, fracture mechanics, you have everything. It's all the physics, really, even plasma physics at points. And so here, the thing is, even though this is a thermomechanical simulation, you can see that the SPH formulation gets a little bit more complex than the original problem that I was showing earlier in a couple of slides ago. And so even though this is thermomechanical, this is already getting complex. And the reason why the GNet method worked very good for the prior example was because the points were fixed in space. So the SPH method actually behaved very similar to the finite volume technique that the GNet method was originally built for. So in this scenario, applying the GNet method actually becomes a little bit more difficult and more involved, and actually it turns into what we call the projection tree reduced order model. Okay, and so here's a link, or not a link, kind of the information to our paper, to the archive of the projection tree reduced order model. It's currently in review at JCP, but we're really excited about some of this the results that came out of here. So if you're interested in learning more, feel free to look into this paper that we have on the archive.
Can I ask a question?
Sure.
One question was in the Petrogalerkin, the test basis was actually the residuals. So you had the phi, which is a trial basis,
right?
And then your test basis was R of U, the residual.
So yeah, sorry about that. So at this point, the trial basis actually comes out of the Gauss-Newton problem, where it's actually I think it was phi transpose, exactly. The A is yeah, that's right. So it would be phi transpose times the Jacobian, and that's kind of the test basis.
Can I give a little background on this?
Sure.
This is Nasir from NRL. So this is indeed a strange choice, and we have been working on this for quite some time with Sarbel Farhat group from Stanford, and this has been a discussion point for some time. But it has been shown that the residuals actually work very well, even it looks counterintuitive. We have not really faced a case where they do not work. It's kind of an awkward choice, but there is really lack of a better choice at this point. But this is something that we're exploring in the future. So actually change what to be using there.
Right.
And the other, thank you. And the other question is about the projection tree. Where's the tree?
Yeah, we're actually, I was just about to start sharing that.
Oh, okay.
Yeah. Sorry, it's a bit of a long kind of context and background. There's a lot of work that came to try to get to that point. All right, so let's see. All right, so here's the tree. Here we go. All right, so unfortunately, we don't have the PT ROM working for additive manufacturing problems yet. So we're currently working on that, but we do have it for vortex dynamics problems that are kind of motivated by this type of problem. The flow past an elliptical wing that generates these types of tip vortices. And so, simplifying this further, we can actually see that the tip vortices act like some sort of two-dimensional projection, a set of particles that interact and repel against each other. And so really, this is a very silly toy problem that we've been working on, but it's very easy to generalize our method on these types of problems that we have here. And so we've actually been working on these types of methods to kind of improve the PTROM, but now we're deploying it on additive manufacturing problems. And so let me just get straight to the actual.
Sorry, we lost you in the most critical point. We couldn't hear you. Can you?
Oh, I'm sorry.
Repeat. Where's the tree?
Yeah, we're getting to that now. Yeah, let me just go ahead and skip to that part then, right? So this is the type of problems that we're working on that we're really motivated by vortex dynamics in aerospace engineering. And so, all right, so the PTROM, the way it works is step 1 through 3, which is the training of the state vector to the hyperreduction, works very similar to the GNAT method. The only difference here is that the tree comes into play when we're trying to figure out the dynamics of our neighbors. In the Gauss-Newton method, we know who our neighbors are, but in a meshless method that has neighbors that move around, we have to query and actually project back to the high dimensional state to figure out where these neighbors are, right? So we have to project back and actually query the points and try to figure out at which sampled residual has what neighbors. And so this is where the tree comes into play. What we do is actually we use two different types of bases, right? We use one to approximate the state vector, which is the target particle, and the other one is instead of using the regular state vector, or sorry, the regular POD basis to project back to the high dimensional state, what we do is we project back to the neighborhood low dimensional state. And so this is done by clustering the tree, which is what you're seeing in this particle domain. So tree methods, the way they work is that you perform some sort of data structure where, say, for example, this is the particle that we want, or that we're interested in querying. We have to understand the interactions of the neighbors to this particle. But instead of actually using, say, for example, this is a distribution of the POD basis, instead of kind of querying the actual individual particles to this particular target, what we can do is actually query the neighborhood instead. So kind of do some sort of agglomeration that's very similar to single linkage or something like that, but with respect to the distance of this particular particle. And so what we're using is two different types of POD bases. One is the state vector POD basis, and the next one is the neighborhood POD basis. And so we can substitute that into the pairwise interaction of the summation problem so that we can basically track, the interaction of neighborhoods with a specific particle. And so what ends up happening is here is the vanilla POD basis that's called by the GNAT method and a meshless method for moving domains, right? So here this represents the high dimensional back projection to figure out who is my neighbor in the actual evolution of the full domain. But in our method, we actually just back project to the neighborhood dimensions. So here you can see that the red particle only has a few yellow points that are close by it. So this is like the regular high dimensional back projection, but the other particles don't really contribute to that specific particle. So you can actually cluster those as a neighborhood instead, right? So that's kind of where the name projection tree reduced-order modeling comes from. And hopefully, you got a little bit more of an understanding, but actually let me show a little bit more about this tree. And so in the case of the vortex dynamic simulation that I showed earlier, you have a nested loop that's quadratic and scales with the number of particles in a domain. So you actually, are performing a quadratic summation. But in our case, we're doing what I call a hyper-reduced pairwise loop, where you're where you're performing a nested loop over sparsely sampled targets that result from the hyperreduction, and you're looping over a clustered number of sources that are a result from the tree decomposition in the POD space. And so the GNAT formulation looked as follows, right, where you're projecting back to the high dimensional state to query the neighbors, but now the PT-ROM looks as follows. And I mean here, this is a very tricky, this might actually be bad wording here, where we say it's N independent, but I don't mean we achieve like, scalar or, a constant, complexity, algorithm, of course not. But what we do here is that it doesn't depend on the number of particles. It actually depends on the dimensions of the basis, of the residual basis and the POD basis that we're using and the hyperreduction particles that we're using. So this actually scales very similar to the original formulation of GNAT, but for finite volumes. So this is actually working very nicely. And so we've applied this method to a multi-query context in the archive paper that we have online. And again, in very simple problems, but in this scenario, we can see that the PT-ROM works very well because it's able to capture the path trajectory at a multiscale, because here we have very slow moving particles, but towards the center, we have very rapid moving particles. And the trajectory, the mean absolute trajectory error was less than 0.1%. And of course, the Hamiltonian with respect to the full order model was less than 0.1%. And in this scenario, we only saw a speed of about 4, and there's a reason why that is actually. But here we have hyper-reduced, the number of targets has been reduced to 12% of the original particle size, and the number of sources have been reduced to 46% of the number of particles in here. So if you do the square product of this, you're going to end up with this type of complexity. And so we actually ended up doing some scaling experiments to see how this scales with increasing number of particles on different vortex problems. And we saw that at one point, we actually got over 2000x speed up the wall time, which was really exciting to see. In this scenario, we actually saw 0.9% of targets with respect to the full order model and 5.6% of sources in the full order model using the clustering algorithm. So this obviously reduces the complexity by a significant amount. And we were able to outperform the original GNet method formulation by an order of magnitude, all at less than 0.1% error. And we even compared this to traditional, hierarchical decomposition techniques, which we outperformed by quite a bit as well. So I think this is pretty much all I have, and I guess I have a lot of room for questions here. But our contributions are basically that we've introduced a new class of model reduction techniques for n-body problems. In other words, these are meshless techniques, and this method is very generalizable across different meshless problems. The results show very, very promising performance in both wall time savings and error. And we have the first application of projection-based model reductions with SPH in an additive manufacturing setting too. So clearly, there's a lot of work that we have to do since this is a new class of model reduction techniques. There's a lot of things we have to address, further addressing, for example, how tree decomposition impacts error bounds on these methods, and other theoretical foundations that we actually have to establish. But we're currently trying to implement the PT-ROM on multiphysics SPH, and we're further exploring the applicability of this PT-ROM on other types of digital twins and other multi-query problems. So thank you so much for your time, and it looks like I finished quite a bit early, so I have plenty of room for questions. So yeah.
Thank you very much, Stephen. That was excellent overview. You covered a lot of ground, and I just want to add that the GAPI POD that you show in one of your slides, I don't know if you know it, but it was developed right here at Brown by Larry Sirovich.
Oh yes, yeah.
About 30 years ago.
Yeah, I remember that. Yeah, yeah. It was done on the eigenfaces, right?
Actually, it was done in several papers. One of them was he was trying to, from satellite images back then 30 years ago, because of the clouds, he had areas which were not covered. So that's how he introduced the broken norm, the GAPI norm, and then he did a POD on that and so on. But yeah.
Very cool. Yeah, I knew Sirovich was big in the hyper reduction stuff, which really motivated a lot of the discrete empirical. I forget what that acronym stands for, but DIME and UDIME and all that.
Yeah, so you use the mask. You need to have the mask. I guess that's how you zero out all the.
That's right.
Make it normal. Yeah.
That's right. Yep.
Thank you, Stephen. We'll wait for the questions from the audience.
Minlang has Minlang, maybe you can tell Stephen all the work that you're doing with SPH and for solids and for fluids and so on, and what we're trying to do with DeepONet.
Oh, sure. Very cool.
Maybe we can talk offline. It's a little bit complicated, so
Sure.
I'll be more than happy to introduce about our recent work.
Yeah, absolutely.
Yeah.
I mean, I think
great talk.
Thank you. I think, yeah, Professor Karniadakis can send you my email and then we can get in contact.
Can I ask a general questions?
Sure.
I'm pretty interested in the mesh-free method. I'm just interested in why. Is there any specific reason you choose SPH? Because there are a lot of mesh-free methods.
Oh, absolutely. Yeah, and maybe I forgot to mention this, I don't remember, but so SPH probably has one of the biggest followings in the meshless community. I'm not sure if you're familiar with the community that's called Spheric. I don't know what the acronym stands for. I'm not really good at keeping up with acronyms. But Spheric is a community that has a lot of members that have open source technology, like benchmark examples, experimental problems like, flow past a cylinder, a dam break, and all that stuff. So SPH has been pretty versatile and very well, distributed across different types of physics. And since we do multiphysics, it seems to be the method that pops, everywhere. It's everywhere across the different multiphysics problems. So it seems to be one of the most versatile meshless methods. And this is kind of, I guess, why we chose SPH.
Oh, I see. Because I read from a paper saying that SPH may suffer from some tensile instability, that kind of issue. So.
Oh yeah, well that's one of the things that I mentioned is that SPH has a lot of room for improvement. So by no means is SPH a fully formed, established problem that is applicable to any sort of problem. There's actually a lot of grand challenges in the SPH community that are well defined, and actually dealing with these types of instabilities and consistency problems is an issue that's currently trying to be addressed. And so it's not a very mature technology compared to other types of frameworks, but it is a method that seems to have a lot of promise to it. And so it's one of those techniques that is currently developed for very specific applications, but there's a lot of room for improvement.
Okay, thank you for your thorough answers. Thank you.
Of course, yeah.
So Stephen, I have a question about the SPH, just following up Kaiji's question. For long-time integration, do you do anything special? Because if you have this course and you have the Laplacian, you can show in the standard version that totally goes to error 1. Mm-hmm. So you need either to remeasure, you need to have some corrections that people have introduced. But we had the one student who was here, and he works now, he's a staff at Sandia. Mm-hmm. So they started with that, and then they developed this generalized least square method, mm-hmm. that basically can go to any order of accuracy, and also they have guarantees that you get the long-term integration. Yes. You get the Laplacian to be bounded errors. But the standard, the point is the standard SPH mm-hmm. will give you a Laplacian which has order 1. Mm-hmm. So if you have Navier-Stokes, for example, after long-time integration, you get nice pictures, but you get big errors.
Right. Yeah. No, so no, you're absolutely right. And in meshless methods, there's something called symplectic time integration, which actually conserves a lot of the structure in these types of meshless problems. And there's actually a lot of work done by Jan Hestave in symplectic model reduction that actually aims to address that issue. So that's definitely one of the things that we're trying to look at, right? So like I mentioned before, there's a lot of work that we still have to do in further establishing the error bounds to this method. But this is basically, this is the beta version. This is not even deployed yet. This is a lot of work that we still have to do. So yeah, that was actually on the kind of like the list of laundry list of things we have to do. And the other thing is also looking at things like baking in structure preserving things in some sort of optimization way or optimal way. So a lot of work by Kevin Kralberg has addressed the issues with GNAT method by baking in structure preserving methods into this hyperreduction technique via some sort of constraint optimization. And that's another way of kind of ensuring long time integration issues that you're talking about.
We had a speaker from Mike Shields from Johns Hopkins, who has been doing UQ on using also these nonlinear manifolds. Mm-hmm. And so I asked this question about, you can think of this as really hugely underparametrized, this ROM, right? Underparametrized representations as opposed to modern neural networks, which are hugely overparametrized in terms of generalization. Mm-hmm. So the question I have is, have you tried to look in the parametric space, how this generalizes for unseen data for inside and outside the parameter range?
Yeah, so actually, so this paper that we're writing, so we haven't done it for the PT-ROM, but we've done it with the GNAT method, right? Which is, steps 1 through 3 in the PT-ROM. So here we're basically trying to identify the heat profile of this additive manufacturing simulation. So the actual profile of how the Gaussian distribution of this is, right? So we're trying to figure out the parameters of this Gaussian distribution and the velocity of it. So in that sense, I think the most I've done, which is of course very small in the parametric space, is dimension 3. It's still very small. Clearly there's a lot of other parameters that we can perform on. But so far, we've been able to maintain accuracy up to a 3-dimensional problem in parametric space. And so we were able to deploy the ReducedOrder model at points it wasn't trained on. And we actually also did in this paper that we have, we did it for a, let's see, where is it? This is why you should not have animations. Let's see. Here we go. We actually did do it for multi-query problems. In this case, it was only a two-dimensional multi-query problem. And unfortunately, all this is done on MATLAB, so we really couldn't push the bounds of performing more.
Stephen, here you are still within. You're not outside the distribution, right? You're within the distribution.
No, so the training points are the blue points. So we're outside of that training points, right? So we're not inside of the training points. We're outside of the actual training points. Is that what you're talking about? Yeah. Yeah. So at this point, we were still able to kind of achieve, decent error, right? So this is the training grid, I should say, right? Oh, sorry, not the training grid. This is the multi-query grid. So here are the training points.
Yeah. This is outside. Yeah.
That's outside, right? So that's as most as we've gotten. It's fancy, but again, there's a lot of work that we still have to do.
Hi, Steve. I have one quick question, just out of curiosity. So basically, we're trying to use SPH to simulate the like the fracture for a hyperless material.
Mm-hmm.
So just out of curious, so because in fracture, so even if you have like two particles that is within the neighbor that is within a very short range. So, but actually, when the pairwise string is greater than some critical point, then there's no interactions, right? So because of the fracture. So I was curious if your method could handle this situation, or is there
Yeah, I mean, we're still looking into that. I mean, that's a very good question, and of course, this is why I'm saying, this is kind of why I alluded to this earlier. This type of meshless approach is like not really available or applied to a lot of traditional resource modeling fields, and so we haven't tested things on that type of fracture mechanics problem either, right? So the problem with the fracture mechanics problem that you're talking about is that SPH really relies on support from its neighbors, right? And so you have to have a certain amount of particles within the neighborhood to actually inform a specific particle of what the dynamics should be. And in that sense, of course, there's a lot of room for innovation in reduced-order modeling with that sense. So we haven't tried it with other types of problems, but that's definitely something we'd be interested in looking at. And we can also follow offline if you want, and try to see if we can have a good discussion on that. But it's a lot of work to do.
Yeah, because you were mentioned the additive manufacturer, and you say that there is a fracture in this problem. So I was wondering.
Oh no, I meant that in the sense of that additive manufacturing is all the physics. In this sense, I'm only looking at thermomechanical simulations, right?
All right.
Yeah. No, I mean, I wish I would have had that.
Yeah, Minglang, we have other efforts that focus on fracture mechanics. So the PT-ROM have not really transitioned to that level, to the fracture mechanics level. But out of curiosity, what type of criterion are you using to release the particles on your fracture mechanics model?
Well, I just set a critical value for the pairwise string. So when the pairwise string is greater than some value, and then I set there's no interaction between these two particles.
Okay, I say that. Okay.
Yeah, but there are many ways to decide that, or based on the energy and a release rate, or but
yeah, that's a very loaded topic. Yes, of course. Okay.
Yeah.
Professor Kanedakis, actually, Stephen had a question from you. Is that what is the full form of crunch?
What's the question? What's the name of crunch? Why crunch?
What does the acronym stand for? I tried to figure it out.
Stephen, crunch is, you crunch numbers, right? Because everybody back then when we started, everybody named their center for non-linear complex systems, right? Something like that. Mm-hmm. And I'm a contrarian. I didn't want to say the same thing. So, but of course I couldn't say that we are a center for simple linear systems, which would be the opposite.
Yeah.
And then I would get no funding from anybody. So instead we say, okay, we are not the thinkers. We are the people who crunch and get things done and so on. So
yeah.
So that's kind of, but here we are 35 years later, still crunch.
No, that's good. That's good. Yeah. So actually, I had an acronym that if I got to lead a group, I would call it the Scientific Computing and Applied Mathematics Research Group, which stands for SCAM. So I don't know if that would work with program managers.
Yeah, you wouldn't get any funding either, or maybe you get.
Yeah.
But everybody would know you.
Yeah, definitely.
Steven, that was excellent. I think. Thank you very much for giving us this. A quick overview of all this. This is this sort of philosophical question I always have, and just following up on my previous comment about Johns Hopkins University, we're actually pursuing now this issue of underparameterization versus overparameterization, and what is the so we have a reactive system, advection diffusion reaction, and it's like flow past the cylinder that you show, but with reactions and so on. That
right.
The Johns Hopkins University has a 600, I think, simulation. So they did the reduced order modeling, and they didn't go outside like you did. You were more brave than them outside the range of. So we want actually to check if DPONet, which is an overparameterized reduced order model, trained similarly. We're currently, Somdata, who is the host today, is involved in this with a smart Greek PhD student that Mike Shields has, Katiana. We gave a talk. So we'll keep you posted, because it's an ongoing work. I don't know actually, how. Because as you know, also machine learning and neural networks have been oversold. But people insist on overparameterization, like people like Tommaso Poggio and others, smart people who say that the power of generalization comes from overparameterization, and Hinton himself, he claims that, he's again, all these applied statisticians always told him to use less parameters than data, and if he had done that, there would be no neural network. So he always used the analogy that our brain has 10 to the 14 parameters, but we only live about 10 to the 9th, or some of us, the lucky ones, 2 10 to the 9th seconds. So if you count every second as an experience, as a datum, you have, let's say, 10 to the 9 seconds, but you have 10 to the 14 parameters.
Oh, yeah.
So, and I think we're doing pretty well so there's like this philosophical question, which is reduced order modeling underparameterized versus overparameterized.
And George, why don't you have another loop on the outside to compute the right number of parameters? This is John Mikopoulos.
Yes, John. You mean for each one of these networks that we overparameterize?
Yeah, I mean, maybe there is an answer to really casting the problem on the meta level and running the same optimization problem, but not really on the physics, but on the architecture of the network.
Oh, yeah, yes. You're thinking much higher. I thought you just keep track of the parameters to see actually how much the overparameterization helps you. I think that would be. But I did some study after I heard Hinton, and basically it's if you look at all the species which have, from the honeybee has 100,000 neurons, we don't know the synapses for all these species, but if you give me, I have a relation now, empirical relation. If you give me the number of neurons of a species, which is not the turtle is an exception, but any other species, I can tell you how long they live.
Okay.
Yes. So I came up with a correlation. Of course, we have 85 billion neurons, which is much less than the synapses. But I'm saying that for each neuron will have at least one synapse. So that's a lower bound. So there is some correlation to this big high-level picture for over-parameterization for true intelligence.
Yeah, I've also, speaking of the over-parameterization and under-parameterization, I've actually been interested in kind of the intersection of some of these methods that have used, for example, nonlinear manifolds as their trial bases or test bases, and kind of in that sense, kind of using over-parameterized data to find this low-dimensional embedding. So I think that's also interesting where, the two kind of hit each other. So, using nonlinear manifolds discovered by some of these networks. So
Stephen, that's exactly the point. Actually, what is the final manifold if we can quantify it, right?
That's right.
Yeah, that's exactly the point. Yeah.
Yeah. So in this sense, the manifold should really be the dimensions of the number of parameters you're looking at, right? So that should really be the dimension of the manifold. If you're looking at 1,000 parameters, then you should have 1,000 dimensional.
Yeah, but that will be good for fitting, but not for learning. Learning is basically you want to have the freedom to visit places that you wouldn't ordinarily.
That's right. Okay, I see.
Yeah, but thank you very much again. That was excellent. Yeah,
absolutely. Thank you.
Thank you, everybody.
Yep. Thank you.
Thank you, John. Thank you, Stephen.
Yep, absolutely. Thank you.
So our next speaker, okay, I can see him online. I'll just make you the co-host, Panos.
Okay, thank you. So, let's see.
Can you try sharing the screen once?
Yes, I have it here. So can you see the screen?
Yes, maybe we could have a full screen.
Right, I'm trying to go there to full screen because sometimes let's wait. Does it work?
No, I don't see a full screen.
You don't see a full screen? Okay, then maybe let me go first to full screen and then share it. I never know exactly. Stop share. Okay, let's go then to full screen first. Okay, and now let me try to share. Does it work now?
Yes.
Yeah?
Yes.
Okay.
Absolutely.
Okay. Great. All right. Okay.
Thank you.
Yes.
So before you begin, I'll quickly introduce you to the group.
Oh, thank you.
Okay. So our next speaker is Panos Stinis, who specializes in scientific computing with application interest in model reduction of complex systems, multiscale modeling, uncertainty quantification, and machine learning. He studied aeronautical engineering at the Technical University of Athens, Greece, and earned his PhD degree in applied mathematics in 2003 from Columbia University in New York in the area of model reduction. He began his career at Lawrence Berkeley National Laboratory and the Stanford Center for Turbulence Research, where he worked on applying model reduction methods to hyperbolic systems and in developing techniques for locating and tracking singularities of partial differential equations. In 2008, he became a faculty member at the mathematics department at the University of Minnesota. Later, he moved to PNNL in 2014, where he is currently leading the computational mathematics group. His research interests include multiscale modeling, uncertainty quantifications. He serves as the co-director of physics-informed learning machines, multi-institution collaboration, and leads the Digital Twin Component Development Thrust of the Energy Storing Material Initiative. And today he will be presenting us on the topic titled Optimal Renormalization of Multiscale Systems. And with this, Panos, you may want to start your presentation.
Thank you very much, Samdata, for this very nice introduction and the long one. So thank you very much for the invitation and everyone for attending. So what I would like to talk about today is optimal renormalization of multiscale systems. And this is a loaded title, so I'll start unpacking it progressively. This is joint work with Breck Merris, Jake Price, and Madeline Shapiro. And it is work that started a long time ago, and it has been supported in its different phases by DOE Oscar Applied Mathematics. So let me start first with what is the problem that I will be looking at. So let's start with the notion of multi-scale systems. For some reason, I'm seeing this whole bar on top there. I don't know how to make it disappear. Let's see.
Does it work now?
Oops. Wait. All right. Okay. So for let's see. Too many things from Zoom. Okay, so many real-world multi-scale time-dependent systems are too large or too expensive to simulate for long times. And what we try to do with model reduction is we want to keep the important features, whether they're scale, structures, patterns, and account for the rest in a simplified manner. However, there is an observation that comes once you start playing around with model reduction is that except for special cases, it is not easy to guarantee the stability of reduced models. So we have to do something about that. And the main idea is the following, that we're looking at a system that, as I said, are too large or too expensive to simulate for long times. So inevitably, these systems, which are the full order system, will run out of resolution, okay? So the main idea that we have explored is that while this full order system is still valid, meaning that it is well resolved, one needs to monitor accurately the transfer of activity, and that could be mass energy, between the resolved and the unresolved scales. The resolved scales are the ones that you are going to keep. The unresolved scales are the ones that you are going to model somehow in a simplified manner. And once you have this information, which is dynamic information, you want to use it to renormalize the reduced model. So this is the first time I'm mentioning this word renormalization. And what does it mean in our context? That instead of keeping the model as it is, you will embed it in a larger class of models where you will allow in front of the different terms to have extra coefficients which you can use to adjust these coefficients in order to be able to reproduce this dynamic behavior. And the hope is that by doing that, you will be able to obtain a reduced order model, which will be able to move forward past the time when the full order system stops being valid. Now, an important remark here is that I'm talking about monitoring dynamic quantities, for example, rates of change. This is not only reasonable, but exactly because we're looking at most of the cases at non-equilibrium settings, this is necessary. Because when you're looking at non-equilibrium settings, the notion of the path that the system follows is important, and that is a dynamic quantity, and that includes rates of change. So, first of all, in order to go to this normalization, we need to have a formalism that allows us to do model reduction. So let me start with that. And I will be using the Morris-Wansink formalism, which goes back 60 years actually to 1961 and the initial work by Wansink. And then, of course, it has been rediscovered and reformulated, and it has been used a lot, especially in the last 20 years. And the main idea is the following. Suppose that we are given a capital M dimensional system of ordinary differential equations, which is written here, du dt is equal to r of u of t, with some initial condition u of 0, u sub 0. And what you would like to do is you would like to construct a reduced order model for a subset of this vector of dimension capital M. Now, exactly because the systems that we're looking at are usually nonlinear, what we would like to do is that if we try to do this reduced order model, we will have to introduce some kind of projection. And as we know, projections do not work well with nonlinearities. However, they work well with linear operators. So the main idea behind MZ is to transform this original system of ordinary differential equations into a system of linear partial differential equations, which live only on the space of all the possible initial conditions. So that's how you go here and you write a collection of capital M linear partial differential equations by using this operator here, the Liouvillean operator, okay? And once you have this collection of systems, this collection of linear partial differential equations, then you can start introducing the concept of projection. In particular, if we take the initial condition U0 and we break it up into two parts, U hat sub-0 and U tilde sub-0, where U hat sub-0 is capital N dimensional and U tilde is M minus N, then we can define a projection operator from the space of functions of dimension capital M to dimension capital N. We need to define also the orthogonal operator, and then by following the standard, basically a variation of constants or the Duhamel principle for partial differential equations, or the Dyson formula that people use in high energy physics, you can decompose the right-hand side of this partial differential equation into three terms. And the reason I've put it and written it in this way, let me explain. The first term here, which involves the projection, is usually called the Markov term, and it has to do mostly with the dynamics of the resolved modes. The second term here, which involves a different evolution operator, which involves the orthogonal projection, is usually called the noise term because it has to do with the unresolved variables. And then there is the third term, which is also the most difficult term to get, which, as you see, first of all, is not local in time, but it involves the whole history. And this is called the memory term. And as you expect, if you have a term that has to do mostly with the resolved variables and another with the unresolved, you need a term for their interaction. And that's what the memory term is there for. And that's why it's so difficult to get. Because if you decide to break down a system into two parts as resolved and unresolved, it doesn't mean that the system wants to be broken down. So that's where the memory comes in to tell you how this is the history of the interaction between the resolved and unresolved variables. However, there is a very good property of this decomposition that we can use it as a starting point to construct reduced order models based on mathematical, physical, and numerical observations. For example, short memory, long memory, etc. And there is another very nice property that these reduced order models, they come directly from the original equations, and the terms appearing in them are not introduced by hand, thus helping then to study the mathematical properties. So but like I said, the memory term is very difficult to get in general. So a lot of people have introduced a lot of different approximations. One approximation that we introduced together with Jake Price in 2019 is called the complete memory approximation, and it's based on this multi-scale assumption, which says we are looking at systems where the resolved and unresolved variables evolve on comparable timescales. So we're not assuming a short memory like is done in many cases. We assume that they involve on comparable timescales. So if you make this assumption, then the easiest thing that you can do, which is not necessarily the best, is to take these two operators here, this operator e to the t minus SL and this operator e to the SQL, and expand them in Taylor series around s is equal to 0, where s is equal to 0 is exactly the current time. And if you collect all the terms, then you get this messy expression here. And then, of course, you say, all right, I will have to truncate this infinite sum series at some point and get my reduced order model. Well, if you try to do that, you find out that the first term that you get is indeed projected, because you see that at the left end here, you have a P, which is a projection. Sorry, here you have a P, which is a projection. So this means that this expression is only a function of the resolved variables, so you can code it and you can run it. And this is known as the T model. However, if you go to the second order term, you see that one of the terms has indeed a projection, but the other does not. Immediately, this involves all the variables, so it's not closed. So what do you do about it? Well, if you take a look closer at this term, you find out that if you take this expression e to the TL, LPL, QL, etc., that this is nothing else but the right-hand side of the equation for the evolution of this quantity. So you can write down the equation of the evolution of this quantity, and you can play again the same game. You can apply the MZ formalism to this equation, and you can do again the Taylor expansion. And if you keep only the first order term, then that's how you close it. And of course, you can do that. This construction can be generalized to higher order terms. And as you understand, very quickly, this thing becomes very involved if you try to do it by hand. However, Jake came up with a very nice way to automate it in Mathematica in a few lines. And it is very convenient considering how involved the higher order terms can be. I can tell you that they get very quickly very messy. So after you have done that, you can truncate the expansion, say after n terms, and you do obtain a reduced order model, which you can then run. And you think, okay, that is it. Now I have my reduced order model. It's closed. It's nice. Let me run it. And it is based on the assumption of absence of time scale separation for most realistic, which is appropriate for most realistic systems due to the tremendous range of scales involved. And if you try to apply it, let's see a very simple example. We'll take the inviscid, well, not simple actually, the inviscid 1D Berger's equation, ut plus ux is equal to 0. We use it with periodic boundary conditions, with an initial condition, which is a sine of x, and with this initial condition, it develops a shock at time t is equal to 1 here. So what we have here is the energy in 16 of the Fourier modes. And this is the evolution of the energy according to the exact solution, the green one. Then we have the red one, which is this model here if we truncate it to n is equal to 3. And what we see is that it cannot go past time t is equal to 1. It blows up. And this black line here, which has the little r in the legend, is the renormalized third order model. So what I would like to talk about is how you can take this unstable model and how you can renormalize this so that you can actually get something which is much better. So let's consider the renormalized model. As I said, at the beginning, how does it work? You take the model as it was before, but you embed it in a larger space of models where in front of the terms here that have to do with the memory, you introduce these extra terms which will be adjustable and also be functions of time in general, so that this reduced order model can reproduce certain dynamic quantities from the full order model while that model is still valid. What I have chosen here, which is a very specific choice for this renormalization coefficients, is that I have introduced a time dependence which involves this parameter capital tau. So if you remember when I talked about the title of this talk, which is loaded because it had multiscale, renormalization, and optimal, I have already explained what is multiscale, what is renormalization, and then the optimal has to do with choosing the value of this parameter tau, because this parameter controls the decay of the memory. And I will give you at the end reference to a paper where you can look more at the details.
Panos, can you give us a little more motivation from this form? Why choose this form? I know you said I chose it.
Oh, why did I choose this form? Yes, yeah. Exactly because we use the Taylor expansion here, which uses t to the I.
Right.
We wanted to have a term that somehow controls the memory of the different order terms. That's why we introduced t to the minus I tau, and we were very greedy. We wanted to have a tau that will work somehow for all orders. Okay, that's why we introduced a very simple power law t to the minus I tau. So if you multiply it with t to the I, you can group it together as t to the...
And tau is greater than 1.
Okay, no, tau is between 0 and 1.
Sorry, but tau between 0 and 1. So,
Yes.
so you have the,
Yes,
okay.
yes. So for tau is equal to 0, you get back the original Taylor expansion. And for tau is equal to 1, you cancel completely this t to the I.
Yeah.
Yeah.
Okay.
Yes. So, and the idea is that you want to estimate this thing. You want to estimate the AI, which is the prefactor, and tau on the fly while the full system is still well resolved. Remember that to go back to this example that we had here, we want to use information before time t is equal to 1 only, right? We put this restriction on ourselves, and later you will understand why, because we want to look at systems.
Panos, how do I know when I will blow up? Do I have a precursor?
Oh, yes, because the T-model term actually, which is the first order term, for these particular cases that we're looking at, you can prove that it is strictly non-increasing. So you can use it to monitor when your system becomes under-resolved. Okay? All right. So I have to tell you, how do we actually estimate this AI and this tau, all right? And like I said, we would like to look at dynamic quantities. So in this particular case, we looked at the rate of change of the energy in a particular mode in the full model, okay? Remember, K is a mode, or one of the resolved modes. And if you're looking at Fourier, it's one of the Fourier modes that you resolve. And you can write this change of energy, the rate of change from the full model. You can get it easily just by multiplying the right-hand side by the complex conjugate, and then this here. And in the reduced order model, for each term in the series, you have a contribution to this rate of change. So if you put them together in a very simple quadratic expression, what would you like to have? You would like to find this A, which is the vector of the prefactors, and the tau, such that this expression here, which is how well the reduced order model reproduces the rate of change of the energy of the full model, is minimized, okay? And when we say minimized over what? You want to collect the rate of change of energy over a collection of time instance t star, okay, where we have collected the energy rate of change, and you want to sum this over the resolved modes, which is F, in our case, capital F. This is very...
Can you go back? Can you show us in the blow-up figure that is very pedagogical? Yeah, can you show us where would you apply that here?
Yes. So for this particular case, we know that the shock, for example, forms at time t is equal to 1, which is here. So we will be collecting only between 0 and something which is close to 1. Okay, so this t star, which is the collection of times that we will have, will only be between 0 and something like, depending on your resolution, it could be something like 0.99 or something. So you want to have enough resolution to get close, but not necessarily cross the singularity.
And in this time, yeah, sure. But yeah, in this time, how many Ks did you get? How many the resolved modes?
Oh,
what do you have as a resolved mode?
Oh, here for this example, I had 16 Fourier modes.
Okay.
Yes. For this example, I'll show you results with different resolutions, and I'll tell you also what is the delicate part, which was my next remark, which is coming here.
Okay.
You set this up, however, once you try to use it, you realize that life is not so easy. So the estimation of AI and tau is delicate, to put it mildly. We still haven't resolved fully the problem, but I can tell you one of the main reasons why we think this is happening. The reason is the following, that because we're using a Taylor expansion, as you look here, what we're trying to do is we're trying to do some kind of regression where we're using here the variables that we're using are t to the I mainly, but because you have different powers of t, these are dependent somehow. And the moment they are dependent, you get into the problem of collinearity when you try to do the least squares problem. So the matrix that you get for your least squares problem is extremely ill-conditioned, and that's why we are only able to get reliable estimates for tau and AI only for small resolutions, okay? So this is a problem that we are currently working on how to resolve. We have several ideas. If I have time at the end, I will tell you a couple of ideas. But let me just move for the moment to show you results, first of all, for inviscid burgers, where we know a lot of things. So let's see how we can apply this thing, first of all, for the renormalization of the 1D inviscid burgers equation. Let's take again the simple initial condition sine of x. We know everything about this kind of initial condition. We know that it develops a shock at time t is equal to 1. In logarithmic time, this is 0, which is here. You see that this is the logarithm of the energy of the resolved modes. In this particular case, I'm plotting for n is equal to 14, okay? And we have chosen the optimal tau. And what do I plot here are the evolution of the energy for a reduced order model with 14 Fourier modes, but of 4 different orders. And I plot the evolution of the energy all the way up to time t is equal to 1,000. So remember, I used only data between 0 and 1, which is 0 in logarithmic time, and then I used it to extrapolate all the way to time t is equal to 1,000, by which time, as you can see from the logarithm of the energy, there is practically no energy left into the system. More than 99.5% of the energy has left the system by then, because it has been eaten up by the shock. What we see from here is that because we're using a smooth initial condition, and this will be very important for later, the renormalized expansion is perturbative. In what sense? If you look at the first order result, this is here with the circles. And if you look at the second, third, fourth order, they all converge. They converge as you go up in order to the exact evolution which is given by a second order upwind solution. And you do get indeed very close to the theoretical slope, which is t to the minus 2 for the energy decay. And this is not just in the eyeball norm, but we can go to the next couple of slides to actually show that we're getting quantitatively really good results. First of all, however, let me say something which is very important, which is the following. All this renormalization business is based on some kind of underlying scaling assumption, okay, and scaling laws. And indeed, if we take these renormalization coefficients and we plot them as a function of the resolution and for the different values of tau, we can find extremely robust scaling laws, okay, which are functions of the resolution, as you expect. And what you see also here is that as you go up in orders, they're very robust, okay? These are the exponents for the different order terms. They're very robust. And if you look at this table, you can see that roughly these exponents go as minus I, so that if you take the renormalized coefficient and you multiply it with t to the I, together, they come together and they form here, and you can define a new time scale. So this new time scale, which involves both the resolution and the optimal tau, is a renormalized time, and it corresponds exactly because capital N is larger than 1. So it's the new time scale is a coarser time scale, and it has to do, like I said here, let me just go back to show it again, with the memory. So what is the actual meaning of that? This is actually very important. we have a simulation which is running for the resolved model, for the resolved modes, but you see that there is this new time scale, which is a slower time scale, which has to do with the interaction between the resolved and the unresolved scales. And what it says is that as you increase your resolution of your reduced order model, this interaction with the resolved scales, with the unresolved scales, becomes slower and slower. So there are two basically time scales introduced effectively in the system, the one of the resolved modes, and then a new one that has to do with the interaction with the unresolved modes. So this is, if you are familiar with high energy physics, there is a celebrated theorem there called the Appelquist-Caraccione theorem, which says that when you renormalize and you have, there they say low energy, here we have smooth initial conditions, there is essentially a decoupling of the small and large scales except for renormalization effects. And this is exactly the renormalization effects. So in other words, and to put it plainly, you can never get rid of the memory, but as you increase your resolution, you have this way to gauge how important your memory is, even though you can never get rid of it completely.
Panos, this is,
Yeah.
let me, you remember back in CM4 where we're doing
Yes.
the molecular system. This was exactly the point with John Lee when we were coarse graining beyond 10 to 1, we
Yes.
would see huge memory effects in DPD. Otherwise, non-memory DPD would work fine, but when we are aggressive in coarse graining,
Yes.
you bring in the memory.
Yes.
So
Yes.
here you quantified. But
Yes.
my question is here, what was tau? Do you have the tau? Is it tau changes from as you change n also?
Right. So again, because it is very delicate, what we have found is that tau itself is a mild function of capital N. Okay. In fact, because we want things to be here non-dimensional, it's a mild function of 1/n.
Okay, but
Yeah.
but what was the value? It was close to 0, close to
Oh,
1?
no. For this, for Berger's, it turns out to be close between 0.3 and 0.4.
Okay, so it's,
Yes.
it's closer to 0. Yeah, okay.
Yes,
okay.
yes. So, right. Yeah, I forgot to say that. Thank you. So, like I said, it's not just for the eyeball norm. We can actually look, because as I showed before, for smooth initial conditions, we have a perturbative expansion. We assume that the fourth order model, which is the highest we went, is the most accurate. So now what I show here is the evolution of the energy for the fourth order model when we use different resolutions. And you see that the results are equally good for many resolutions. And this thing here, this which is not accurate, is what you would get if you used 16,384 Fourier modes, but in a brute force calculation which uses no memory. Okay, so in this case, you would go a little bit after the singularity, but then you become completely, the prediction becomes very wrong very quickly. Now here I have on the right the relative error for the different resolutions, and what is interesting is that, remember, we are calibrating between time 0 and 1, and we're integrating all the way up to time 1000. And we see here that for the resolutions 10, 12, and 14, even after time 1000, especially for the 12 and the 14, your relative error does not grow to more than 5%. Okay, so this is, for me, it was very impressive given that we only calibrated using data back here very close to 0. Okay, now let me show you also something interesting about the prediction for inviscid Bergers, about the contribution of the different terms to the rate of change of the energy. This is again logarithmic time between time 0 and time 1000. And the shock forms at time t is equal to 1, which is logarithmic time is at 0. The peak of the shock is at time pi over 2, which is here. Okay, and here we have the 4 contributions. This is the first order term, second, third, and fourth. And then we add them all up together and we compare them to the actual correct rate of energy contribution given by a second order upwind solution. So you see that all of them come together with the right sign, and they give you a very nice prediction of the actual rate of change of the energy all the way up to time 1000. And now, since this goes back also to George's favorite question, which is, can we actually extrapolate? Okay, we calibrated a model only using sine of x. What happens if we try to use this model and try to use a different initial condition? First of all, because of the inherent scaling laws, if I use, for example, an initial condition like sine 2 of x, I can very well get equally good results as these ones here, just by doubling the resolution of my model. And if I use sine 3 of x, again, I will get equally good results if I triple the resolution. But what happens if I take an initial condition, which is sine of x plus sine 2 of x? This is much, much more difficult. And why is that? Because this is a nonlinear equation, and you have two shocks now, which are not going to be standing shocks, but they're going to move towards one another and actually interact. So without any calibration, but by using a scaling argument to obtain the renormalization coefficients for this particular initial condition, we run the model and we get the following result. We start with a very small error, which suddenly spikes to about 25%, and then it comes down and it remains to something like a few percent all the way to time 1000. So why is that? The reason is the following. We're using here a very, very small resolution. For sine of 2 of x with capital N is equal to 12, the effective resolution that we're using is something like 6. So I have a movie here where you see the prediction of the fourth order model up to time 10. You see that even with this very, very low resolution, which it's not, to give you a nice presentation of the solution, it can capture actually the interaction of the shocks and give you the one shock, which later it's a standing shock that starts heating up the energy. So this was the evolution between time 0 and time 10, which is, oops, sorry about that, which is where we got this spike here. And after that, it gets the standing shock and it keeps eating up the energy in the correct way all the way up to time 1000. Okay, so again, we have a very, very small resolution, so don't expect to see anything very smooth, but it is interesting that without any extra calibration, we're able to get not just standing shocks, but now interacting shocks. Okay, so let me now move to a problem where instead of knowing a lot of things, like the 1D Berger's equation, we actually, despite a lot of theoretical effort and a lot of numerics, no one really knows what is happening. And that has to do with whether the solution of the 3D Euler equations, incompressible Euler equations from fluid mechanics, develops a finite time singularity from a smooth initial condition. This is one of the main problems, open problems in PDE theory. This is the equation here. It is in 3 dimensions, and it's a 3-dimensional velocity field. This is the pressure. This is the incompressibility condition here. And we used the simplest possible, very smooth initial condition, which is the Taylor-Green initial condition. Now, for this very innocent-looking initial condition, even the largest supercomputers stumble after a few, relatively few units of time. They run out of resolution, okay? So what we are trying to do here is we're trying to see if we can get a reduced order model which remains at least stable for a long time. Again, if we play the same game, here we only had data from a small calculation which was for the first maybe a couple units of time. And we played the same game. However, exactly because we didn't have a large computation to get closer to the singularity, we couldn't get really the optimal tau. So here we just chose one value of tau, and we plot the scaling laws for the renormalization coefficients, and we indeed get, again, very robust scaling laws. And two remarks: each higher order exponent does not alter the previous orders, as you can see from here. And as you will see in the next figure, there is again convergence of the behavior of the energy as we increase the order of the reduced order model. And something that I have to admit, it made me happy. This is, at least to the best of my knowledge, the first time that a renormalization scheme for the 3D Euler equations was constructed, which actually includes all the complex dynamics present in 3D Euler. So let's see what this thing looks like, okay? I don't have here, again, I don't have solutions in real space. I can only show you things about the energy, okay? Because we're really looking at very, very small resolutions, okay? So there is no really any point in looking at a 3D domain with such a crude resolution. What we see is that, first of all, like I promised in the previous slide, as we increase the order, there is indeed convergence of the models, okay? And the second is that, which is very interesting, is that as we increase the resolution, even for these low resolutions, there seems to be an increase at the actual rate of energy, rate of change of the energy as we increase the resolution, which means that as we go to higher resolution, this reduced order model tells you that there is more and more activity happening at small scales. I'm not saying that this means something for the actual long-term solution and whether there is a singularity or not. We don't have the resolution to say that, but it's an interesting observation. However, let me just show you here something which makes contact with the very large scale computations that people have been doing for the Taylor-Green problem. Here I have plotted the contribution to the energy rate of change from the different terms in the memory, like we did for Berger's. So we have the first order term, the second, the third, and the fourth. And when we put them all together, we see here that there is a peak. Well, it's negative. So the highest value in absolute value of the energy rate of change happens somewhere between time 8 and 9, and it is about here minus 0.015, okay? So we got this result with a calculation on a laptop that took a couple of days. So the largest calculation that I have seen for the Taylor-Green problem came out in 2020. They used 100,000 processors for a calculation that ran for a few days, and they got the result here for the peak with the value 0.016. So I think it is again impressive that with such a small calculation, but I think that with a well-calibrated renormalized reduced order model, we are able to reproduce integral quantities like the energy rate of change. Okay.
Again, so you're,
yes.
you're actually, you're showing that there is singularity then. Like you before with the Berger's equation, you said here's what the shock is. Time equals 1.
Well, in that paper, they call it actually towards converged calculations which suggest a singularity, but this is just the contribution to energy rate of change, right? We don't know if actually this corresponds to solution that develops activity all the way down to the 0 scale.
Right.
But
how about the time? You also capture the same time?
Yes. So if you look at, I can give you the reference to that paper, they predict, they went up to time, they could go, I think they were using a discontinuous Galerkin method, which allowed them to go up to about time 20. So, but the peak that they got was between time 8 and 9 also, which in logarithmic time is somewhere here, yes. And they got, for the largest resolution that they used there, this peak that they got was around 0.016, something like that.
Okay.
Yeah. So that is our contact, if you wish, with actual really big calculations. So, and again, if you look at the coefficients here, the coefficients are roughly, again, for each order are roughly to the minus I. So you do get the same coarsening of the time scale. However, I have to say, don't jump into any conclusions about saying that Berger's is the same as Redu-Euler. They're extremely different equations. And even though you may get a coarsening of the time scale that looks similar, the tau is actually very, very different, in the sense that the values of tau that work optimally for Berger's, if you use them for Euler, you get unstable models, all right? So the value of tau is very, very problem dependent, and yeah.
But
Okay.
here you say tau equals 1, which kills the. You mean tau? You found tau 1 to be the optimal?
No. Here we couldn't get the optimal. So I have actually in the paper, we have tried different values of tau, and the behavior doesn't change much. It's just that here I'm plotting it for tau is equal to 1. Okay, but we have found that anything that has tau greater than 0.4 is stable. And if you look at tau 0.6, 0.8, 1, the behavior here is very robust, okay? The behavior is very robust, meaning that the peak is between 8 and 9, and it goes close to this value. So like I said,
so
yeah.
Panos, you may have the $1 million.
No, this is just a very, crude numerical calculation. So, but anyway, I was happy that it made contact with the very large calculations. Okay, so let me summarize. And since this is the Crunch seminar, and in the Crunch seminar, there have been a lot of many talks about machine learning, I will make now contact between what I have been talking about and machine learning. So the late and great Steven Weinberg, whom we lost in July, gave us a talk in 1983 where he called it why the renormalization is a good thing. And in there, he said that for each problem, it is important to concentrate on the relevant degrees of freedom. So this brings us back to the question, oops, sorry about that, here. Oh, I don't know what, can you see? It's just a blank screen.
No, we can see just the heading in summary. In
summary, yes, but then when I try to move forward, what happens?
We can see the screen now.
You can see the screen, but you cannot see the other points here, right?
No.
I cannot see them either. Let me see. Let me try to stop and let's see if I can share again the screen. Okay. Because this is my last slide actually. So let me go to full screen mode. Okay. For some reason, okay. Let's see if I can try to share. Okay. Let's see. Sorry about that. I don't know what happened. It suddenly decided.
Perhaps I have your slides. Do you want to share?
Yes, please. So if you can go, go to the last slide, the next to last, actually, that would be great.
Okay, I'll just do that.
That's the reason why I always send the slides beforehand, because you never know what will happen even on the last slide. So. Yep. All right. One before. All right. Great. Okay. So I was supposed to have this appear individually. Now you have all of them together. So, like I said, it is important to concentrate on the relevant degrees of freedom. And our construction works because we used smooth initial conditions. Smooth initial conditions, however, is something relevant. What does it mean to have a smooth initial condition? It depends on how rough are, what is your resolution? If you have a small resolution, even an initial condition that has a couple of Fourier modes is not smooth. So with this in mind, one can choose variables, for example, basis functions, through machine learning for which the initial condition is smooth. And then you can apply the previous renormalization arguments, which is perturbative renormalization. In fact, if you attended the Crunch seminar 2 weeks ago, Saad Kadir and Breck Maris talked about this kind of work, where we try to use machine learning, and in particular DeepONet, to identify those basis functions so that we can represent an initial condition with relatively few variables, and then we can play the same game with the perturbative renormalization. However, there is a very interesting analogy also between what we have been doing here with the perturbative renormalization and a body of work that was put together by Yuri Manin about 10 years ago, where he actually made an analogy with high energy physics. And he said that in the same way that in high energy physics, when you look at low energies, you can do perturbative renormalization, you can do the same thing if you are in the context of computations itself, computation themselves, meaning that you can take a computer program and you can break it down into parts based on their Kolmogorov complexity, and then you can renormalize it. This is exactly what we're doing here. We're taking a numerical method, which takes a solution at time t is equal to 0 and evolves it, okay? And we go to the right-hand side of the equations, we break it into terms, the memory terms, of increasing Kolmogorov complexity. Indeed, if you look at those terms, that's what they are. And for smooth initial conditions, we can assign smaller coefficients to the higher order terms. There's a lot more to say here, and I think that there is even a connection with deep learning itself, but we don't have the time right now. But I want to say one last thing, which is the following. What happens if all these things break down? If you cannot find any basis to write down smooth initial conditions? In other words, how can we move beyond smooth initial conditions? In that case, as people have done in physics, we have to move to what is called non-perturbative renormalization. What this means in this context that we have here is that we have to go to the memory, and instead of doing things like the Taylor expansion, we have to do a function space expansion of the whole memory itself. And I think that because of the particular structure that DeepONet has, it can be used to obtain a finite rank projection of the memory. And in this particular case, what you will be doing there is feed DeepONet the history of the resolved variables in the branch net, and when you train it, the output of the trunk net will be the vector of renormalization coefficients, and the trunk net will take as input the resolution and the time, so that indeed you will have a nice way to do renormalization in cases where you cannot identify basis functions for which your solutions are smooth. And some data, can you just go to the last slide, where here are some relevant publications for if you're interested. And thank you very much for listening.
Thank you, Panos. Excellent. I'm here with, I don't know if you met Fariba before.
Yes, I've met Fariba actually. Yes,
from the Air Force, because we're discussing the exchange we had a couple of years ago about the Cartix model,
right?
Memory model and so on for LES and so on. So yeah.
Yes.
Any questions for Panos?
Questions? Yes.
I think we went over their head, but although the first part was good, introductory,
I'm sorry about that, but as you see, the first publication there, it says 2009. So this is work that goes back several years. So there is a lot of material there that it's not possible to cover everything, all the details within
I have
45 to 50 minutes.
Quantifying the coarseness and the time scale actually based on the resolution of freedom, and yes. Let's say with this uncertainty about tau.
Yes,
it's really. Did you try for the Burgers equation where you know the answer and everything? Did you try to verify that indeed if you do different modes n, it scales like that, capital N?
Yes. I mean, the scaling laws is what we got, right? I mean, I was inspired to write down this renormalized time scale because of the scaling laws that we found for Burgers. So Burgers does satisfy this roughly, right? Because, like I said, I make the assumption, some data, maybe you can go back to the slide that has the scaling laws for Burgers. It's further back. A little bit more. One more. Yep, here it is. Oh, sorry. One forward. Yes, here. So if you assume that the renormalized coefficients depend on the resolution with these exponents gamma in for the different orders, then you find roughly here that the gamma in are minus I, where I is the order, okay, of the term. So if you put it together with the t to the I, you can write roughly that the renormalized coefficient times the time monomial from the Taylor series can be written like that. And the tau, which we also asked before, is somewhere between 0.3 and 0.4 for Burgers. But it's, of course, like I said, problem dependent. And this is also very greedy. We try to use a single value of tau that will work for all orders, okay? So, yeah.
Also, can I think of T as a characteristic time scale of the fine resolution?
Yes.
And so okay, so then let's call that square root of the time scale of the fine resolution, 1 over n times the square root of that fine scale resolution time. Characteristic time scale.
Yes.
And yeah. So in LES, when we go, let's say 10, 1 over 10, that would be like a coarsening.
Mm-hmm.
I mean, we have to have the ratio actually. So here to make sense, yes, for the ratio of the time scale. So it will be like 10, 1 over 10 square root of time. So you have this much slower, therefore longer, right? Obviously longer.
Yes. So the moment you have a coarsening of the time scales, it means that these unresolved variables the interaction with the unresolved variables is slows down, the larger is the resolution of your reduced order model. But exactly because it goes only as 1 over n, you can never get rid of the memory. So this is a case of incomplete similarity. You can, as you increase the resolution of your reduced order model, the effect of the memory and this slowing down becomes, more and more slow, but you can never get rid of it.
Yeah,
completely. And you can see that in some data, if you go to the next slide here, in this brute force spectral calculation, which does not use any memory, it doesn't matter how large a resolution you use. After the singularity happens, you will lose all accuracy.
One last thing is that Charles Menevaux from Johns Hopkins and Tamer Zaki wanted to listen to your talk, but Charles had a meeting, so he will invite you to give a talk to their fluids group there.
Oh, thank you.
So you will expect, he told me that.
Yeah.
Because recently we started thinking about a Lagrangian model.
Okay.
Not a Lagrangian LES subgrid model.
Okay.
Where we take memory into account.
Mm-hmm.
So Lagrangian. So we have Galilean invariance, but having so we have some evidence that this is the right way to go. So we propose a new type of subgrid which will have memory and so on. So I showed him your paper and he was interested in that.
Yeah, great. Thank you. So yes, and if people have questions later, it's easy to find my email. It's just panos.stinis@pnnl.gov. So please send me any questions that you may have.
Thank you very much.
Yeah.
Some data, maybe you can complete the proceedings today.
Yeah. So thank you, Panos. And if there are no more questions, we can actually go back to our working schedules.